We're going to talk about transformations of sinusoidal functions. We'll graph and transform sinusoidal functions, but we'll always be starting with that base graph, the base graph for sine and the base graph for cosine. We'll be starting with those. And then we'll be involving the same principles that we've looked at for transforming all other functions that we've done before. So we're going to have those same four parameters, a, b, h, and k, and they will do the same thing to sinusoidal functions as they do to those other functions. So we'll be identifying domain, range, phase shift, period, amplitude, vertical displacement of sinusoidal functions. So there's a couple new terms there that we'll talk about. We'll develop equations of sinusoidal functions expressed in both radians and degrees from graphs and descriptions. We'll look at solving problems graphically that can be modeled using sinusoidal functions. And then recognizing that more than one equation can be used to represent the graph of a sinusoidal function. The reason you can use more than one equation, remember, is because the graph of the sine and cosine have exactly the same shape. They have the same characteristics. All that changes is where they start. Okay, so we'll look at that as well. So on the bottom of the next page, you can translate graphs of functions up or down, left or right, and you can stretch them vertically and or horizontally. The rules that we have applied to transformations of functions also apply to transformations of sinusoidal curves. So in this case, we're asked to sketch the graph of y equals sine of x minus 30 degrees plus 3. So this will be a transformation of y equals sine x, which will start with our base graph. Sine always starts in the middle. It has critical points at every 90 degrees. So it starts at 0, 0, and then at 90 degrees, you're at a maximum. At 180, you're back to the middle. Another 90 degrees, you're at the minimum. Another 90 degrees back to the middle. So this is the graph of our base function, y equals sine x. And we're going to transform it to y equals sine of x minus 30 degrees plus 3. Now, at the bottom on the right, vertical displacement means the vertical translation of the graph of a periodic function. So that term vertical displacement is only used when you're talking about sinusoidal functions. And in this case here, because you've got that plus 3 at the end, that's our k value, that's the part that shifts the graph up and down, we will have a vertical displacement of 3 units up. Right? Which determines that horizontal midline. Remember that these graphs have a horizontal midline. Up to now, they have been the x-axis, but now we're shifting the graph up 3 units, which means that horizontal midline goes up 3 units as well. So I've represented that by that broken line. Okay. So the other thing here, when we're talking about sinusoidal function, is a phase shift. That is the horizontal translation of the graph of a periodic function. So that is what the h value, or in this case, the c value, does. Because note how the variables have changed. Instead of h and k, when we're talking about sinusoidal functions, you'll sometimes see different variables used. So instead of h, it's c. Instead of k, it's d. But it doesn't matter what parameter, what letter is used to represent the parameter, it's where it occurs that tells you what happens, right? We've always said before that the h is hooked together with the x, or a plus or a minus, and it's in brackets. Well, now it's a c instead of an h. But it's the same position, it's the same result, which in this case, our value of c would be positive 30, so the graph will shift 30 to the right, which means we'll have a phase shift of 30 degrees right. So our phase shift of 30 degrees to the right. So those are the two transformations that are going to happen in this case. So instead of starting at the point 0, 0, it'll start at the point 30 degrees, 3, because the horizontal midline has now been shifted up 3. Now, also in this case here, our scale isn't really good for starting at 30 degrees, because if you look at what our scale here is, between 0 and 90, it's split into 1, 2, 3, 4 equal sections. So each section will be 1/4 of 90 degrees. And 90 divided by 4 is 22.5. So this first vertical line represents 22.5. So we're going to end up just being to the right of that as our starting point. To the right of 22.5 would be 30 degrees, which is our phase shift. And so instead of ending at 360 degrees, we're going to end at 360 degrees, 30 degrees to the right of 360. Everything is moved to the right 30 degrees. The starting point is moved to the right 30 degrees, and the ending point is moved to the right by 30 degrees. Okay? Also, the halfway point of the first cycle, which is where it crosses the horizontal midline going downwards, will be 30 degrees to the right of 180 degrees. So that's shifted over 30 degrees. My first maximum point, which will be 1 unit above the horizontal midline, our amplitude hasn't changed. Our amplitude is still 1. So normally that was at 90 degrees. It'll be 30 degrees to the right of that. And that'll be at a height of +4, 1 unit above the horizontal midline. Our minimum point of the graph was at 270. Well, again, it'll shift 30 degrees to the right, and it'll be 1 unit below the horizontal midline at +2. So here's the graph of our transform function, one cycle of it, of that graph will look like that. So the domain of this hasn't changed. We just did one cycle, but the graph goes on forever. It'll go from -infinity to +infinity. Our range, though, will change. We have a minimum value of +2 and a maximum of +4. So using interval notation, that's what those would look like. And we've already used our language of transformations to compare the graph to y equals sine x. We've said there's a vertical displacement of 3 units up and a phase shift of 30 degrees to the right. All right? So in this case, we want to sketch the graph of y equals cosine of x plus 45 degrees minus 2. So in this case here, we're going to start with our base graph of y equals cosine x. Remember, our cosine graph starts at the maximum. It still has critical points at every 90 degrees. So the next critical point, you'll be in the middle. You'll be at a minimum. Another 90, you're back to the middle. Another 90, you finish the first cycle at the maximum. So there's the first cycle of that graph. And now we'll apply our transformations to that graph. So the x is replaced with x plus 45, which means that the graph is going to go to the left 45 degrees. Remember, your c value, your h value is the opposite of what it appears to be, because the general equation starts with x minus c. So here our c value is -45, which means we're going to have a phase shift of 45 degrees to the right. left. 45 degrees to the left. And we have our d value of -2, which means we're going to have a vertical displacement of 2 units down. So again, this terminology, phase shift, vertical displacement, is only used when you're graphing trig functions. So because it went 2 units down, our horizontal midline will be now at -2. It goes down 2 units. So all our points are going down 2 units, and we're also shifting the graph 45 degrees to the right. Okay, so the starting point will have to go 45 degrees to the right. The starting point is 1 unit above the horizontal midline, so that'll be now at a value of -1, 1 unit above the horizontal midline, and it'll have to go 45 degrees to the left, which is 2 units on this scale. Again, between 0 and 90 has been divided up into 4 equal sections. That's what our scale is. Each section will be 1/4 of 90 degrees, so 2 sections would be half of 90 degrees, which is 45 degrees. Half of 90 is 45. So that'll be 2 sections, or 2 points on this scale. So 1 to the left takes us here. 2 to the left would be over here somewhere. So we don't really have the ability to put that on here exactly, but it'll be approximately there. So that's our maximum point, 1 unit above the horizontal midline. And then we'll go 90 degrees to the right, which is 4 sections. Okay, so 1, 2, let's do it this way. 1, 2, 3, 4, you're in the middle. Another 4 sections, which is 90 degrees. 1, 2, 3, 4, you're at the minimum. Another 4 sections, which is 90 degrees, you're back to the middle. 1, 2, 3, 4. And then another 4 sections, 1, 2, 3, 4, we're back to the maximum. So this is one cycle of this graph. There's the graph, one cycle of that graph. And the domain won't change. We only graph one cycle, but it'll still go from -infinity to +infinity. But our range changed. Now it went from a minimum of -3 to a maximum of -1. So there's our domain and range. And we've already used our language of transformations to describe what happens. A phase shift of 45 degrees left, a vertical displacement of 2 units down. Okay? So now let's add in changing the amplitude, introducing an A parameter. Again, this will be a transformation of y equals cos theta. So we'll start with that as our base graph. Cosine starts at the maximum. So also notice here that instead of pi over 2, it uses 0.5 pi. It's the same thing, right? Half of pi. But our critical points are every pi over 2. So after the maximum, we'll be at the middle, and then the minimum, middle, and then finish off our first cycle at the maximum. So this is our graph of our base function y equals cosine of theta, or cosine of x. So now we have 3 parameters that we need to discuss. First, we have an A value of -2. So that'll do 2 things. It'll cause a vertical stretch about the x-axis by a factor of 2. And a reflection about the x-axis. When we talk about transformations of a trig function, remember that the a value actually tells you the amplitude. The amplitude of this graph is always the absolute value of a. In this case, the absolute value of -2 is 2. That's our amplitude. Okay, so that was our first parameter, our a. Then we have a c value, and remember the value of c is hooked directly onto the x, or in this case to the theta, with a plus or a minus, and it's inside the brackets. Our c value is -pi. It's always the opposite of what it appears. So therefore, we're going to have a phase shift of pi radians to the left. And finally, we also have a d value of -1, which means we have a vertical displacement of 1 unit down. Okay, Daniel, with us? Are you checking all your stocks or what? Are they up or down? Buy. Time to buy more. So remember that the d value, the vertical displacement, tells us where our horizontal midline is. It's at -1 in this case. So we'll start by drawing that in there. So what's going to happen to our starting point? Right? Our starting point was at 0, 1. So the two things that are going to affect that are the a value. Remember, we've got an a value of -2, so that'll cause a vertical stretch by 2 and reflect it over the x-axis. We said that you can multiply the y values by the a value, and then you can do both transformations simultaneously. So starting at a y value of +1, that's multiplied by -2. 1 times -2 is -2. But then we also have to go pi to the left. So there's our new starting point at -pi, -2. Right? It was a maximum, but now it's going to be a minimum point because it was reflected over the x-axis. Yes, sir. Yeah, you're right, I did. Thank you very much. So now we're starting at -3. So I did the left, but yeah, I didn't go down 1. Thank you for that. Okay, so again, this is a minimum point, right? We started at a maximum, that's where cosine is, but because the graph reflected over the x-axis, instead of being at a maximum, it's now at a minimum. Our period hasn't changed, our critical points haven't changed. Every 90 degrees, or every half pi, will have another critical point. So starting here at -pi, -3, our critical points are every half pi. So our next critical point will be at -0.5 pi. You will be at the middle, which is on the horizontal midline. another half pi, you'll be at the maximum. Now, because our amplitude is 2, our maximum will be 2 units above the middle. The middle's at -1, 2 units above that will be at +1. Another half pi, we're in the middle. Another half pi, we're at our minimum. Another half pi, back to the middle. Another half pi, we're at our maximum. And we can continue a little bit more here. Another half pi, we're in the middle. Another half pi, we're at our minimum. And another half pi, we're back to the middle. So I've got more than one cycle of this graph that I can draw. So there's a partial graph of that function. It didn't ask us to write the domain and range, but let's do it anyways. Just for the practice, our domain doesn't change, but our range does. It goes from -3 to +1. Now, before we go on to the next one, you can use your graphing calculator to check your graphs. So we're going to do the graph of y equals, this is -2 times the cosine. Notice when you hit the cosine, a bracket opens up. So in that bracket, we're going to go x plus pi, and then close the bracket, -1. So we put that equation in there. To make it look like the graph that we have on our page, we need to make sure that we are in radian mode, because our x-axis is in terms of radians. Also, our phase shift is in terms of radians. So we need to be in radian mode. And then our windows, I'm going to go from -1.5 pi, -1.5 pi. And when we put that in there and hit enter, it'll change it to a decimal. All the way up to +3.5 pi. That's the maximum point that we have on our graph. So I'm going to say maximum, I mean furthest to the right. And again, when you hit enter, it'll change it into a decimal. And our scale is every half pi, or pi/2. Also, on our grid, our graph goes from -4 on the y-axis up to +2 on the y-axis. And we can keep our scale at 1. So now when we graph it, it should look the same as our graph. And we can check some points by going into the trace mode. For example, at 0 radians, our y value is +1. So if I let x equals 0, that matches the y value that we have on our graph, +1. Let's check this minimum point here, which is at pi radians. If I let x equal pi, y should equal -3, and it does. So I've checked a maximum, I've checked a minimum. Let's check this point here where x is half pi, 0.5 pi. The graph is going through the horizontal midline where y is -1. So 0.5 pi, I get the right y value, -1. So the graph that I graphed matches what the calculator tells us it should be. So you can always check these on your calculator to make sure that you've put everything in there correctly. Check to make sure you have the right points. All right, so let's go on to this next one then. 2 sine of theta take away pi on 2 plus 2. So again, we've got the 4 parameters. We've got an A, we've got a C, we've got a D. So let's start with our A parameter. Our A parameter is positive 2, which means we're going to have a vertical stretch about the x-axis by a factor of 2. Basically, our amplitude, which is the absolute value of A or the absolute value of 2, our amplitude is 2. So remember, the amplitude tells you the distance from the horizontal midline up to the max or down to the minimum. The next thing we have here is we have a C value of positive pi on 2. Remember, the value of C is the opposite of what it appears to be, which means we're going to have a phase shift of pi on 2 radians to the right. And finally, we have a D value of positive 2, which means we have a vertical displacement of 2 units up, which remember tells us where our horizontal midline is. It'll be at plus 2 in this case. The D value tells you where that horizontal midline is. Normally, for our base graph, which we'll start by drawing first, has the horizontal midline on the x-axis, where y is 0. So again, we're starting with a graph of a sine function that starts in the middle. Every half pi is a critical point. So the next critical point is a max, middle, minimum, back to the middle. So there's our first cycle of that graph. And now we're going to graph our transformed function. So normally the graph starts at 0, 0. It's going to go pi over 2 or half a pi to the right and then up 2 units. So this graph will actually start there. I mean, these graphs of sine always starts on the horizontal midline. And so that is the point 1/2 pi or pi on 2, 2. Our critical points are every pi on 2 or half pi. So if we start at pi on 2, our next critical point will be at pi, and that'll be a maximum, which will be at positive 4 because our amplitude is 2. Another pi on 2 or half pi, we're back to the middle. So at 1.5 pi, you're back to the middle on the horizontal midline. Another pi on 2 will be at our minimum, which again is 2 units below the horizontal midline because that's our amplitude. Another half pi, we're back to the middle. Another half pi, we're at our maximum. So I can go backwards if I want, just so I can get more of the graph. If we start at 0.5 pi or pi on 2, 2, if we back up a half pi, we'll be at our minimum, which is 2 units again below the horizontal midline. And if I back up half pi, I'll be back on the horizontal midline. So let me start that again. All right, so there's the graph, as much of the graph as we can draw with the windows that we're given. And to make sure that that is correct, again, we'll put it in our calculator. So we're going to do y equals 2 times the sine of x, take away, and I'll have to use brackets here because I need to go pi divided by 2. Close the bracket on the pi on 2, close the bracket on the x minus pi on 2, plus 2. Again, I need to be in radian mode, which I am. The windows here go from negative pi on 2, negative half pi, up to 3 pi. I'll keep my scale at pi on 2. The minimum here, I can go from negative 2 on the y-axis up to, say, positive 6. So now when I graph it, it looks the same, but I can check some key points. This graph starts at the point, or not starts, but it goes through the point 0, 0. So if I go into trace, I let x equals 0, y equals 0, so that point matches up. My first maximum point is at pi radians, a maximum value of 4 should be at pi, and it is. My first minimum point here is at 2 pi, and that's, I guess, my next minimum point is at 2 pi. So that works as well. Right, so the calculator graph matches what we drew. So can always use that to check. All right. So now let's add in a b value as well. In this case, we have a b value of 2. But remember, to get the correct h value, or in this case, the correct c value, b must be taken out as a common factor. We've seen that time and time again. To get our correct c value, b must be taken out as a common factor. So to get what's inside the rounded brackets, to get our c value, we have to divide each term by the common factor of 2. So that's why we just have an x there. And when you divide 2 pi on 3 by 2, the 2's cancel, and you just have pi on 3. So that's what that equation will look like. Take b out as a common factor. So if we write our 4 parameters and the effect, first we have an a value of 3. So that's going to cause a vertical stretch about the x-axis. At a factor of 3. Basically, again, the amplitude, which is the absolute value of a, or in this case, the absolute value of 3, is 3. So that's what our a parameter does. Our b parameter is positive 2. So that's going to cause a horizontal stretch about the y-axis. But remember that the scale factor is always the reciprocal of b. it's going to cause a horizontal stretch about the y-axis by a factor of 1/2. So everything will be 1/2 of what it was before. Our period will be half of what it was before. In this case, again, the x-axis is in terms of radians. Our period will now be 2 pi divided by b. Our period is pi radians. And our critical points will be half of what they were before. They're also half. Our critical points will now be every quarter pi, or pi on 4. We've determined that we have a C value of pi on 3, which means that we're going to have a phase shift of pi on 3 to the right. And finally, we have a D value of +2. So we have a vertical displacement of 2 up, which again tells us where our horizontal midline is. Our horizontal midline will be at +2 for our transform graph. But this is a transformation of y equals sine x. So we'll start with that as our base graph. It starts at 0, 0, critical points every half pi or every pi on 2. So there's one cycle of the sine graph. So our new graph, if we take our starting point of 0, 0, vertically stretching that by 3 doesn't change it. Okay? Horizontal stretching by 1/2 doesn't change that point either. But it has to go 1/3 pi to the right and up 2. So if we look at the scale here, all right, between 0 and pi, that is divided into 1, 2, 3, 4, 5, 6, 7, 8 sections. We have to go 1/3 of a pi to the right. So according to this scale, we've got 8 sections. We have to go 1/3 of 8 to the right. 8/3 is 2 2/3. So we're going to start 2 2/3 sections from 0, 0. So there's 1, there's 2 there, 2/3 is approximately right there, and we're starting on the horizontal midline, which is up here at +2. Let me use a different color here. So that's where we're starting. Okay? Our critical points are every 1/4 pi. That's our critical points. Again, between 0 and pi, it was divided into 8 sections. 1/4 of that would be 2. So every 2 sections, we're going to have another critical point. So starting from 2 2/3, we're going to go 2 sections to the right, and that's where we'll be at our maximum, which is 3 units above the middle. The middle's at 2, 3 units above that will be at 5. 2 units away. Another 2 units, we're back to the middle. Another 2 units will be at our minimum point, which again is 3 units below. That'll be at -1. Another 2 units, we're back to the middle. There's the end of our first cycle. Our period we found was pi radians. So that would be 8 complete sections from where we started. So starting here, there's 1, 2, 3, 4, 5, 6, 7, 8. So we ended where we were supposed to end by applying our critical points. So let's continue. Every 2 units, we're at another critical point. So we'll continue that, just so we can get as many cycles as possible of this graph on our grid. I can go 2 units to the left as well and draw more of the graph. Every time I go 2 units to the left, that's another critical point. Okay, so there's our graph. Right, and a little more difficult to check points exactly from our calculator. We can certainly make sure that it looks the same. I will put it in exactly as it was originally written. So it's 2x minus 2 pi on 3, which I put in brackets to keep that all together. Close the brackets on the 2 pi on 3. Close the bracket on 2x minus 2 pi on 3 plus 2. So here I'm basically going from negative 0.5 pi in my windows, negative 0.5 pi on the x-axis, up to 3 pi, which I think is what we had there. And our y minimum, negative 2 up to positive 6, so I can keep that all the same. So that certainly looks very similar to what we have here. Right? If I put in a couple points, for example, if I put in x equals 0 in the trace mode, I should have a value of y a little bit higher than negative 1, and I do, right, between negative 1 and 0. If I let x equal 0.5 pi, I should be right here. I should be just to the left of that maximum. My value of y should be a little bit less than 5 at 0.5 pi. And it is a little bit less than 5. Okay, so you can certainly check some points. You're not going to be 100% sure of your accuracy, but you can be fairly certain that you've graphed it correctly. So we've talked about all of those attributes except for our domain and range. Domain doesn't change, but the range does every time. Here our range goes from negative 1 up to positive 5. Okay? So here's an exercise for you to work on. So it's a math riddle. How often did the student who failed his trig functions test do his homework? So what you're going to do is you're going to match the equation to the graph. So for equation number 1, when you find the graph of y equals 2 sine x, when you find that graph, whatever letter corresponds to that graph, this first graph corresponds to the letter h. So whatever equation matches that graph, if it's equation, let's say 3, that matches graph h. On the next page, you will put an h in the number 3 box. If equation 3 matches that first graph, which is graph h, you will put an h in the 3 box to solve the riddle. Okay? So you'll know you're right if you get the answer to the riddle that makes sense. Okay? So you should be working on that today. We'll do some more work tomorrow with equations of graphs, graphs of equations. Tomorrow we'll look at graphing some, but then also writing some equations as well. Okay? So you should work on that for practice.